Back, level 3 physicists, continuing on with the electricity and electromagnetism level 3 external, focusing on AC circuits at the moment and putting it all together with the LCR circuit. So in terms of summarizing, in terms of phasor diagrams, you can see that the EMF, capital E, across the inductor will lead that across the resistor, okay? Whereas for a capacitor, the voltage across the capacitor lags the voltage across the resistor. Okay, so that basically shows you from the diagram that the voltage across the inductor is completely out of phase, 180 degrees, with the voltage across the capacitor. And what does this all mean? Well, basically you've got to calculate total reactance, and as previously mentioned, the reactance across the inductor and across the capacitor are completely out of phase. That means you can find the total reactance by subtracting the reactance of the capacitor from the reactance of the inductor. Okay, and this of course also means that for this example, that if positive, then the overall circuit is inductive. And if it's negative, this value of the total reactance, then it's going to be a capacitive circuit. So we've seen these before for the RCL circuit and AC. You can measure the impedance associated by the sum of these values, and the impedance for the total resistance in an AC RCL circuit can also use Ohm's law, so supply voltage will be the current times the impedance. So this is quite intimidating in terms of the different waveforms. The focus really should be on the extreme right hand side, this part here. Okay, all that's really saying is that when the voltage across the inductor is greater than the voltage across the capacitor, then the subtraction here occurs in terms of the vectors. And that's basically what I wanted to show by that diagram. Don't be too intimidated by the different waveforms. And the current stays the same. And the voltages across the inductor, as was previously mentioned, and the capacitor are 188 degrees out of phase. So then from vector diagrams, you can see on the right that the total impedance will be the total reactance all squared plus the resistor all squared. Take the square root of that, okay, a bit of Pythagoras. And then also the supply voltage will be the voltage across the resistor all squared plus the voltage across the inductor minus the voltage across the capacitor squared, take the square root of that. And then you can also see from the vector diagrams that tan theta, now the phase angle which the supply voltage leads the current, will be the total reactance divided by resistance, which also equals the voltage across the inductor minus the voltage across the capacitor divided by the voltage across the resistance. Okay, and the final point is going to be around resonance. Okay, so in terms of resonance, as the supply frequency of an LCR circuit increases, due to the equations, the reactance, the reactance, getting confused by terms, the reactance across the inductor increases, but the reactance across the capacitor will decrease. At a certain point, these two values will be the same, and this is known as a certain frequency, the resonance frequency. Okay, that's where the reactance across the inductor equals the reactance across the capacitor. And if you plug in the equations and do a bit of rearrangement, you can see the equation for the resonance frequency. Okay, and that's going to be 1 over 2 pi the square root of L times C. Okay, and at the resonant frequency, two things occur. The two reactances will cancel out, so therefore the impedance is going to be a minimum. And because the impedance is a minimum, that means the current in the circuit will be a maximum. And that, friends, is AC circuits.